Hello, my name is Chung. I'm a brand professor of California Institute of Technology, known as Caltech, and also I'm a JPR research scientist. I'm going to present some recent method that combine machine learning and I can say AI with the control theory and planning, so we can actually get some more robustness out of this learning-based control method. And I'm pretty sure that this method will be also very much applicable to any type of environment, including forest, for this workshop. And I'm going to show you some spacecraft simulators. So this is my lab, and I have some multiple spacecraft-like robots. They are called spacecraft simulators because they can actually float on a flat surface, and they can use these thrusters and reaction wheels so that they can move around and control the orientation. This is relevant to like any motion planning that has to avoid an obstacles because they have to come together in a tight space, and then eventually they even do a docking, but they also do collision avoidance. At the same time, there's basically this is an implementation of our optimal motion planning using sequential convex programming. So I'm going to talk about that too. I'm not going to talk too much about perception here, but we have a significant activity in perception. I'm just giving you some example here. We are using decentralized and some cooperative estimation so that you can actually cooperative fashion, we can estimate the whole swarm shape and at the same time, relative location of your neighbors, here neighboring spacecraft or neighboring robots using some distributed estimation. So again, this is my spacecraft lab. We have a multi-agent systems, and starting from any initial condition, they figure out what's the best collision-free optimal paths. It's a conventional optimal control problem, but we have a way to solve them using sequential convex programming. But there are multiple variations. But at the end, as I kind of implied in my title of the talk, we are going to also show that how we actually incorporate probabilistic constraints or chance constraint, or even like a nonlinear dynamics with a stochastic noise. So we are going to talk about that. But you can get some more information about our prior work for multi-spacecraft autonomous rendezvous docking and sequential convex programming in these papers here. So this is the main message for my talk. And I'm going to show this slide many times. It's a little bit busy slide, but it kind of conveys the main message in the sense that, yes, we have optimal nonlinear feedback controller here, but we can also incorporate some learning-based method. I'm going to talk about that later. We have a dynamics and we have a certain environment. I'm giving you an example of flying ambulance or flying car project that we have in the lab. And we have an estimation theory. So again, as I said, we have a like online learning or offline learning method that can actually improve the dynamics. I'm just here giving you some example of only kind of additive unknown term G function here. We can learn offline. Also, we have some method that can actually adapt in real time. And let's talk about the planning. Yes, this is only feedback control and estimation part. But if you look at this box here, we have also multiple methods that can be used to do a motion planning. So obviously, if you have to fly fast in a very obstacle-rich forest, then yes, you have to somehow have a very good perception method, but at the same time, you have to have a fast in the sense that the vehicle moves fast, but also you have to do a very fast computation to avoid an obstacle. So also I'm saying here that we can also accommodate some learning-based method to improve the accuracy and optimality and safety of your motion planner. Because obviously, if you use some optimal motion planning, using some optimal control-based method, then your trajectory is as good as how good your dynamics is. So obviously, there could be an actual violation of your safety if you don't have accurate dynamics you're using the optimal control. So then how we can integrate all these different pieces together. And my point is that, yes, you have to make sure that they are stable and robust. So you can actually apply this nonlinear stability theory to not only to control, but also even motion planning. And I'm going to talk about that using some stochastic incremental stability theory that I'm going to talk about. I'm just giving you an example here that before I talk about some of my prior work in bio-inspired flight, because that has some connection to this forest motion planning. And here I'm just saying that hierarchical combination is very important. And if you actually talk about the, for example, spacecraft, sorry to say spacecraft, I mean, we already know that there's a hierarchical combination. You have a high-level motion planner and all the way down to the like a motor control for example, reaction here, right? So this hierarchical combination is always used. So when you talk about the like a reverse engineering brain, so that we can maybe use some learning-based method, people only talk about the reverse engineering brain. For example, reinforcement learning is something like what basal ganglia is doing in the brain. But what about the central sensory motor control from spinal cord? So basically, you have a local loop that can actually regulate the muscle behaviors using local sensory feedback. So that can be much faster and self-contained without much brain intervention. So basically, one idea is that this is my prior work. I developed a mathematical model that can represent this like a central pattern generator you can typically find in a spinal cord. So you can generate a self-sustained like oscillatory motions. And then what brain can do is only control the multiple phase differences and amplitude of these multiple oscillators. So it's going to be much less computational burden for brain or main controller, whereas we have a central pattern generator that can actually generate the rhythms for each multiple oscillator. So I apply that to flapping flight, because flapping flight is just not flapping your wings left and down, I mean up and down. It's going to be just maybe 2 off or at most 4 off. But if you look at the bats or birds, they have multiple joints on the wings. And for example, bats do have a 34, 36 degrees of freedom on the wings. And then it's going to be a challenge to control those individual joints, right? Some of them are passive, but if you, at least you have like many active joints you have to control using your muscles or using motors, for example, for robots. It's not going to be computationally tractable. So this kind of idea of a central pattern generator is actually very neat. So we also apply that to like this turtle robot, where we can apply that to control the individual 4 limbs, and each limb has an up and down motion and also load. And then so you have like basically 8 oscillators, and then we can actually do a kind of coordination of these oscillatory motions to control the orientation and the position of your turtle-like robot. So this is a kind of famous batbot. This is a robotic bat with Alireza Namezani, who is now a Northeastern, and also my former colleague, Seth Hutchinson, Professor Seth Hutchinson. In my opinion, this is one of the most advanced ornithopter robot. It's also relevant to forest because if you want to fly your bird-like robot, and you might want to use this kind of a bat robot. And so idea is that instead of just looking at insect-like a flight where you have just like up and down flapping flight, this robotic bat only weighs very little, under 200 grams. And then it can actually flap the wings, and the left wing, right wings are independent. And then also we have like a wing folding, left and right, independent wing folding. So you can actually turn the robotic bat rapidly to the left and to the right. And that kind of a maneuver is very important if you want to fly an aircraft in a very obstacle-rich environment like a forest. And this is a kind of a self-contained robot where we have advanced microprocessor, IMU, some other sensors, and we have, can you believe it? We have 5 independent active motors with the encoder feedback. So you can, it's not like passive motors. So it's a kind of very sophisticated system, but I misspoke earlier. So it still weighs under 100 grams, which is actually impressive. So this is a conventional way of control. You have a feedback control, you have a plant, you have an environment, and you can do some estimation. Typically, for linear system, you do a Kalman filtering or Kalman filter variation, like extended or unscented Kalman filter, and then you can check the stability and of your closed loop or estimator, and then you have a separate motion planner. You can use the kind of RRT randomized method, or you can use some optimal optimization-based method to optimize a cost function, but they are not really integrated. Second problem is that there is no sophisticated like a learning method that can improve your model you're using for feedback control estimation as for also for motion planning. So that might actually reduce the kind of quality of your method. For example, like as I said earlier, your optimal trajectory you compute might not be optimal, or it might actually violate the safety because you use the wrong model. So what if you can update your model you're using for optimal control, like for example here, G, using some learning-based method, and that kind of method also can be applied to feedback controller. But anyone can do that. You just add some like a learning block using some training method, but you have to kind of ensure the safety when you combine this kind of black box, like a deep neural network, for example, with some controller or motion planner. Right? So that's something that I'm going to talk about. This is a little bit cheesy slide, but I want to talk about some flight dynamics. Again, I'm kind of talking about more aircraft or aerospace application for forest. And this is actually a Pelican that was stranded in Tanzania in Africa, and even forgot how to fly, how to flap its wings so they can fly. But it's all of a sudden kind of realized how to flap the wing in left and right. And then it's a beautiful motion. And I want to say here is that those left wing and right wings are not mechanically connected. So as I shown earlier in my robotic pad or our robotic pad example, they are independent, but we can actually control those multiple joints using synchronized controller, for example, a central pattern generator, for example, artificial central pattern generator. So one example is actually this particular aircraft inspired by bird flight. And as you can see, this one doesn't have a vertical tail. Means if you know the flight dynamics, if you don't have a vertical tail and rudder, you cannot really control the heading or yaw or directional motion of your aircraft. Also, you have less stability because you don't have a damping in the heading motion. So
to demonstrate the capability to perch on a human hand. A typical perching maneuver consists of a gliding phase, which brings the aircraft suitably close to the target. Thereafter, it pitches up to a high angle of attack and decelerates rapidly as it perches on the target.
Yeah, so we developed this aircraft and motion planner and feedback controller. We actually have a sophisticated controller using dynamic inversion, but essentially what we are demonstrating here is that you just throw a glider. Of course, we are kind of getting help from like a biphone feedback system to get the state information, but we are demonstrating our feedback controller and motion planner so that we can steer this glider that doesn't have a vertical tail, so it's unstable in terms of a heading, but you can use the independent left wing and right wing to control the heading control to steer the glider to desired position, for example, human hand, right? Which is actually impressive maneuver for such an unstable aircraft. So this kind of a agile motion is very important when you actually have to fly an aircraft or anything in a very obstacle-rich environment, but if you are flying that very fast. I want to also take this opportunity to kind of talk about another application of a bio-inspired flight, but this kind of combination of bio-inspired flight research and also kind of swarm research and motion planning. So bird strike is a major problem. It causes a lot of financial damage. If you look at this miracle of Hudson River, obviously it was spectacular landing, happy ending, and also there was somewhat lucky because the captain was familiar with a gliding flight from his military training. But oftentimes, I mean, sometimes we don't get a happy ending. So how can actually use this bird-like on airplane to herd, steer flock of birds, not just single bird. We have a flock of birds away from the airfield so that we can prevent the bird strike. It's a crazy idea, right? So, but I think we can also find a great application of this real-time motion planning, right? Because you have to really figure out the right path for this UAV to herd flock of birds. And typically people have used shotguns and sidens and even real Pelican Pelican to scare away these flock of birds. But they're expensive, and I mean this Pelican Pelican is an endangered species. So you want to actually develop a solution using robotic bird to herd the flock of birds. So believe it or not, we have developed a method. We actually published in the Transactions on Robotics. So basically, it's a first-time demonstration and development of methodology to herd the real flock of live birds using UAV. So we can see that from this video, we are actually effectively herding a flock of birds by changing the direction, by actually scaring them away. And we actually reverse engineer this flocking dynamics, how they react in response to the predator or pursuer or threat. And also, if you actually penetrate the flock too fast, they're going to spread the flock or spread the swarm, so it's going to worsen the problem, right? So you have to make sure that you don't perturb too dramatically, but you kind of check the boundary. So it's kind of called the wave. Our method is called the wavefront algorithm, so they can actually herd a boundary of the flock of birds. So that's another application. So this is a real video we demonstrated in Korea. So basically, this is a dot here. Our drone is basically herding a flock of birds. So this is also my prior work published in the International Journal of Robotics Research, and it actually has the title Forest. So like a ghost shark flying very fast in a forest, it actually avoid an obstacle while it's flying really fast, right? So how we can actually implement this kind of motion planning? And also this kind of aircraft has the sensing limitation like range and bearing field of view limitation. So one idea is that any aircraft has a time delay. You want to turn, but then there is an actuator delay. So you're going to actually move a little bit forward and then turn. So we actually usually take into account this kind of a nonlinear time delay in your dynamics. And then you develop this kind of like a pursuit evasion, like a Dubin's vehicle motion planning. And so you can stitch over this multiple turning algorithm, but what's innovative here in this work is that if you figure out that, there's no kind of safe path, you can do like aggressive turnaround maneuver like you're doing here. We experimented validated that. So that you can kind of avert your current path and then come back to the original position, and then you find another path so that you can safely move. So you kind of stitch this turning algorithm and also with a 3-dimensional agile aggressive turnaround maneuver in a very dense forest, you can actually plan this motion so that you can eventually, on average, you can actually fly much faster than you are just moving forward without this aggressive turnaround maneuver to reassess your flight path. And then they can be formulated as kind of a parameterized time delay between elevator deflection and aileron deflection so that you can actually control the shape of your 3D turn maneuver, and they can actually approximate this optimal control solution basically to complete the 3D turn. And so again, you can kind of combine the aggressive turnaround maneuver with basically forward flight, and that duly take into account this actuator time delay, and then we can actually plan a very fast maneuver in an obstacle-rich environment. So going back to this one, let's talk about a little bit about motion planning. So how we can actually combine learning with motion planning. This is a conventional optimal control problem. I'm just going to give you a little more complicated problem where you have a multi-agents, a swarm. So this capital N is the number of agents. So this is typical optimal control problem. You have to minimize the collective cost, and you have a highly nonlinear dynamics. So that's another challenge. And obviously input is constrained, and then you have other state constraints. The primary example of a state constraint is actually this collision avoidance, but as you know, this is a non-convex because you have to stay outside. Another thing is the like a terminal initial and terminal constraint, but as opposed to a single optimal trajectory, if you actually maneuver multiple spacecraft in a forest, you have to make sure that you have to assign the target course if they are going to a different target. So again, you can actually have some target assignment problem. because as long as they kind of shape into a different shape, you don't really care if agent one goes to a particular location, as long as it's shaped into a different target shape. So that's another complexity coming out of that. So we have a method of solving that complicated real-time optimal control problem using a set of sequence of convexification and solving convex optimization problems. So it's called the sequential convex optimization problem. And then we also take into account other methods and other constraints you didn't originally have, so that the optimal convex optimization problem is actually feasible and also stable. And another thing is that, as I implied earlier, the target assignment, so your goal can be actually assigned and computed using some separate process, like a high-level process that can run in a much slower. So kind of that implies the multiple time scales of your learning and control method. I'm here saying that in this case of multi-agent coordination, you can also run the, like for example here, assignment method. We have used the Hungarian-based method, also game theory-based method. They can run much slower because in this case, you just figure out the terminal location at terminal time instead of every time step. So that's much slower decision than that kind of implies that you can kind of mix this much slower learning with a much faster low-level motion planning. So this is a kind of example we published in International Journal of Robotics Research 2016, where you have multiple agents with even nonlinear dynamics. We can actually have them like reshape into a different shape or a different configuration while they are avoiding collision, make sure that they avoid the collision, and also minimizing certain cost function like a control cost function. So I'm going to talk about the couple of extension of this sequential convex programming used for solving real-time nonlinear optimal controller, which can be used for motion planner. One example is that in terms of collision avoidance, we do a hyperplanar approximation, so they can be very conservative in a very obstacle-rich environment because it worked very well in open space. So what you are doing is a spherical expansion. So okay, you can use some kind of a graph-based approach where you can generate the certain path that optimizing certain cost function. Maybe you might not actually use the dynamics. Then you find certain paths, and then you expand the sphere along the chosen path using real dynamics and more rigorous constraint, like I was doing earlier in the sequential convex forming. And that way you can actually find an optimal path. So as opposed to drawing the hyperplane approximation with respect to all the different obstacles, you just draw the sphere, you just expand the sphere or ellipsoid along the path. So it becomes like a tube, and then you solve the optimal control problem using sequential convex forming. So I'm going to talk about how we can extend this using some learning. So we talk about the optimal control problem, but oftentimes the dynamics are perturbed by stochastic noise. So you have to write the actually it's a stochastic differential equation. And because state is actually unknown, and also dynamics, because not because of the state estimation error, but maybe dynamics itself is actually perturbed by noise. And also maybe you have some uncertainty in the certain parameters. So you have to maybe use chance constraint, probabilistic constraint for defining safe regions, inequality regions. So it's actually called the chance constraints. So how you're going to solve this complicated optimal control problem to find the optimal path in the presence of stochastic uncertainty. So what's new here is that actually Yasuo Naka, we have this CDC paper called the trajectory optimization for chance constraint nonlinear stochastic systems. And also recent extension where we actually combine this method with the learning is going to appear in robotics and automation matters. So idea is that you can actually turn this nonlinear stochastic differential equation into the deterministic equation using this polynomial chaos approximation. It's kind of conceptually similar to Galerkin projection, where you can turn the stochastic differential equation to deterministic ODE. Then you can also convert these chance constraints into some deterministic constraints. as you can see, then you are actually solving the deterministic nonlinear optimal control problem there, where you can use the sequential convex forming. I want to also take this opportunity to talk a little bit about the some of the research activity. We are actively working on the flying car, flying ambulance. What's new here is that instead of have a single loader or big gigantic loader like a helicopter, we have a distributed electric propulsion. So here we have like 8 propellers, and we also have a wing, which means that you can actually fly longer distance because you don't have to just use the propellers to move forward. You're going to get a lift out of the wing because we are going to have a sufficient flight speed. And it actually poses unique control challenges here. So this is our flight task where we validated our nonlinear flight controller that can enable safe transition from the vertical takeoff and also even vertical landing to forward flight using fixed wing. So kind of having this kind of stable transition is the kind of holy grail of this VTOL with a fixed wing. And that kind of other winged VTOL or multi-loader is kind of a popular example of a flying car, as you know. So we have a laboratory setup where we can actually test multiple multi-loader system with a wing. And we actually have validated a fully autonomous flight 5 miles, 2.5 miles back to back. And then eventually safe landing. Here we are actually demonstrating kind of fault tolerant control. What if you have random failure in one of the loaders or maybe multiple loaders? And because we have multiple loaders, we can kind of reconfigure the controller very fast so they can actually still have a safe fault tolerant attitude and position control. So we have worked on these multiple models of this fixed wing multi-loader, as we are seeing multiple examples here. So again, as I said, I mean, this might be useful for fast flight in a forest where you have to have a rapid turn. So you might actually get help from this multi-loader system, but at the same time, in order to have an endurance, a longer flight distance, you need to have a wing. So that's the difference between just purely multi-loader system and multi-loader combined with a wing. So we have this IJRR paper just presented in 2020 IJRR, where we developed the sophisticated nonlinear control method and adaptive control that incorporates 3-dimensional flow sensing to improve the transition flight. So again, this is that experimental results. This is the adaptive nonlinear control that incorporates the 3-dimensional flow measurements. For example, we measure the angle of attack and the side slip angle, and also the forward speed using this 3-dimensional flow sensor. And we incorporate those measurements directly to improve the or update the estimate of certain aerodynamic parameters so that we can enable this smooth transition. So you might actually see this is a kind of conventional rotorcraft flying. It's actually more than that because you can see this big gigantic fan array here. It has a 1,298 computer fans. Oops. And so this is basically a treadmill for aircraft because we are demonstrating the basically fixed wing aircraft, almost like a flying like a stationary fashion, like a hover, but it's not really using the rotorcraft to make it hover, but basically it's using the wing-borne lift generated from this airflow coming from this fan array. So it's almost like a wind-based treadmill, and we can generate the disturbance and in addition to the main flow speed, where we can actually test our adaptive control method. So this method actually shows that it can actually outperform conventional PID control. So I had some technical difficulty here, but I'm back. So this is also kind of fascinating kind of a research project. We have a walking and flying robot. It actually has leg joints, but it has actually 4 propellers, so it can be used as a kind of a pod rotor. So it can actually walk and like a jump, and so you can actually you view this as kind of adaptive landing gear if it's a flying vehicle, and you can now do a skateboarding, and you can like walk on a rope. So we have a different maneuvers that hopefully next opportunity we are going to show you to you. Yeah, so this is another video that our Leonardo like walking flying robot actually walking. So the idea is that we have a synchronized propeller control with a leg joint control, so that we can actually improve the stability of walking using thrusters, basically propellers. You know, any environment actually. So let's talk about some learning-based flight control method. And this is called the Neural Lander. And the key idea is that we want to learn some unknown dynamics model. So we are taking an example of landing a drone, because when you land a drone, there is actually a ground effect, additional force, actually because of the kind of reflected air flow from the these loaders, multiple loaders. So the closer to your aircraft to the ground, the stronger the external disturbance generated as a ground effect. So we learn the model using deep neural network. The problem of this kind of method is that you don't really know how large the output is. If you actually especially go beyond the original training bound, for example, you landed at a certain velocity or certain state, distance and height, but if you go beyond that training region, then you don't know what's going to be the output. So we actually using this particular technique called the spectral normalization, so that you can actually bound the Lipschitz constant of this black box, deep neural network. And we are nonlinear control expert. So if you can actually basically bound the slope, then we can use the information to design the stable nonlinear controller, right? So that's the idea. So if you look at the video, it's called the Neural Lander. We published that in the 2019 IJRR, and you can read the paper and then associated the video. So you can see that compared to the conventional PID controller, it actually lands much smoothly, and it can actually get closer to the ground. Again, this is called the Neural Lander, where we use a spectral normalized deep neural network combined with a nonlinear controller to improve the tracking control performance. So another example is the basically scanning the ground closer. Then you can see that you have a much smaller error, tracking error, as opposed to just conventional PD or PID control. The nice thing about this spectral normalization is that, as you can see from this plot, if you go beyond the training region, training domain, you can kind of see that there is a more smooth kind of a relationship. So your prediction coming out of your deep neural network is actually smooth and more correct. Whereas if you don't have a spectral normalization, you cannot really predict what's going to happen. And another example of experiment is that you scan over the table. So whenever you experience a ground effect, our deep neural network can accommodate a sudden change in the force, and by correctly predicting that. Actually, I saw the heat map. So you can see that you can correctly predict the shape of your table if you are considering the ground effect. So nice extension of that is that what about a swarm? Because you have like a downwash coming out of swarm, so you cannot really fly these multiple drones close to each other because there is like enormous amount of this downwash. So similar to the using the neural network, to predict and fit forward cancel the ground effects, we can also use this downwash prediction using deep neural network. With the key idea is the spectral normalization, so that you can actually design the smooth nonlinear tracking controller when you have multiple drones. So it's called neural swarm. and it was presented the 2020 ECLA. And the one extension of this spectral normalization, so new idea in the neural swarm is that you have to use a deep set, because you have this permutation invariance, because when you have multiple agents, the downwash or this interaction, aerodynamic interaction, actually are permutation invariant. Like you don't really care, agent 1 is here, agent 2 is here, so you have to have some permutation invariance. Then we are using this deep set. The idea is that if you have a deep neural network, superposition fashion, obviously this is a permutation invariant, right? And then you have the summation of this deep neural network into the another network deep low, so that you can actually have this permutation invariance with respect to this relative vector xji. So that's the main idea. Quite intuitive, but it hasn't been explored in this multi-agent system community. So this is the first paper that exploit both deep set and also a spectral normalization for learning-based flight control for multi-agent drones. Another extension is that when I talked about the neural swarm or neural lander, we're basically talking about offline training. You collect a lot of data, and then you can actually estimate the additional force coming out of either interaction with neighboring drones, downwash, or ground effects, like environment, like flying close to the wall or flying close to the ground. Here, what if you have an external, like a wind disturbance that's not controlled, or that's not perfectly dependent on your state, like a velocity, speed, or distance to the ground, or distance to the other neighbors. It's just wind blowing, right, and randomly, and it's not really state dependent. Right? So you have to adapt your prediction of your disturbance in real time. So it's called a neural fly. So basically a combination of spectral normalized neural network trained offline and combination with meta learning methods, so that we can actually update some of the weights in your neural network using a meta learning method. But here, you cannot do that. You cannot completely do a real-time backpropagation to retrain the neural network. So what you're doing is actually you only train the last layer using some combination of adaptive control. So we are now demonstrating this neural fly method here. And then when you add these multiple blocks of learning for motion planning and also feedback control, that example I gave to you, you have to ensure that this black box, or if there is a deep neural network, and oftentimes for perception community, you use a convolutional neural network. This black box shouldn't destroy the stability of your estimation or learning system or feedback control, right? So oftentimes they are kind of stochastic in the sense that it might be governed by stochastic nonlinear dynamics or uncertainty in your state estimation. So estimating the stability of nonlinear stochastic dynamics is not a trivial matter. So we have some tools to use that for that method. So just a quick overview of nonlinear stability theory. You know the Lyapunov-based method. Basically, you compute the scalar function that can get you the stability of your nonlinear dynamics. So as long as your scalar function, for example, like a mechanical system or a Lagrangian system, if that scalar function or Lyapunov function is monotonically converting to 0, then your system is kind of asymptotically stable, or can also characterize exponential stability. What's new in the contraction theory, originally proposed by Jean-Jacques Slotin and MIT, and with Winnie Lohmiller, is that we want to check the study incremental stability of multiple trajectories. So it's not just about stability about equilibrium points. Rather, I want to check the multiple trajectories. So I'm going to tell you why that's important. Another important point is that it's a global if you have no perturbation. And then you can also extend that to the bounded input, bounded output stability, because the stability out of contraction theory is exponential and global. And it's actually easy to combine multiple systems. So for example, if you use the passivity, I don't know how to use the passivity to prove the stability of a hierarchically combined system, but it's kind of trivial if you use the contraction theory, as you can see this in this example. So how can you quantify contraction of your nonlinear system? So its idea is very simple. You actually get this virtual displacement vector, as you can see oftentimes in the calculus of variation. as long as this infinitesimal displacement delta x is converging to 0, then basically any trajectory from any initial condition, they are converging to the single trajectory. And then you can check the generalized Jacobian. As long as that's uniformly negatively definite, you can actually see that the system is contracting, which means that all the trajectories from any initial conditions, they are converging exponentially fast to a single trajectory. So why that's useful? Because as you can see that if the original system is exponentially stable, and now you have a bounded disturbance, then you can kind of characterize the kind of bounded input, bounded output stability. And also you can do that with the L1 or L2 integral. So basically you can see the bounded input, like a finite gain LP stability, if you have a system without disturbance exponentially stable, which is contracting. So you can kind of use a comparison lemma to characterize this bounded state or bounded output with respect to bounded input. So why this incremental stability is important? For example, for tracking control problem, essentially you want to have these 12 trajectories between your original trajectory from your dynamics controlled and some desired trajectory. If you are talking about the estimation, yes, you want to have your estimated trajectory converge to your real dynamics trajectory. So it's almost like a synchronization. So if you remember this work, my original paper in 2009, a paper with Chung, we actually proved the combination of tracking control combined with the consensus, nonlinear consensus synchronization. So you can do some time scale separation so that you can actually have them synchronized faster than tracking control. So that way you can actually characterize this robustness of your nonlinear controlled system. And same thing can be applied for estimation problem, right? I mean, you have a basically nonlinear dynamics, which is actually process, propagation step of your estimation or Bayesian filter. And then you have like a measurement update, right? Or Bayesian update. But then when you have a nonlinear dynamics and nonlinear measurement model, and you have to somehow, you have to ensure some stability. So you can actually use this kind of stochastic nonlinear stability theorem to prove the stability of your nonlinear observer. So let's talk about some stochastic stability theorem a little bit. So this is the original paper by Chung. So if your original system, x dot g of x, is stable or contracting with respect to certain metric here, n, so it can be used for proving the stability of your original system. Now you stack the same dynamics perturbed by a noise. So this is a Wiener process and some different weight here, B1, B2. And then you can see that if your original system without noise is contracting, which is exponentially stable, and they are converging to some single trajectory, then noisy trajectory like A and B, they are also contracting to each other, but because of the noise, they are not perfectly converging to each other, but they are going to converge to a certain Q exponentially fast in the presence of noise and in the mean squared sense. So that's this theorem here. So you have two trajectories that are converging to each other. So mean squared error between A and B will be exponentially bounded by this non-vanishing term like a C there. And then you can actually compute that rather rigorously. So the new contribution of this paper, I'm citing here like Donnie and my name and Seth, publishing Transactions on Automatic Control. We kind of extended this original Chung-Jak's work with a farm to include state-dependent metric to prove the stability. But the actually main contribution of this paper is actually applying that method, stability, to observer design, where you actually can rewrite the nonlinear dynamics with a state-dependent coefficient form, like x dot f of x, but rewrite f of x with the a of x and x. So probably you might remember the SDRE controller or SDRE filter. But prior to our work, there's no kind of rigorous way of determining what kind of a of x is best, because there are multiple a of x that satisfy f of x. So what we have proposed here is that, yes, we can actually propose some convex combination of a different a of x, and then there might be some certain constraint on rho, this coefficient, which is from 0 to 1. and um, and then you make sure that this is kind of A of X and the B of X is actually, or C of X is co-estimator. It's kind of observable. So there might be some constraint. And we formulate the optimization problem so that you find the optimal law that can minimize certain error, like the estimation error and so on. So this is the now convex optimization problem where you minimize the mean squared error, steady state error, whereas where you can actually make sure that it actually satisfies certain LMI constraint coming from your deterministic stability theorem and the other bunch of constraints, because you have a law and multiplied by this Q matrix here. It's actually bilinear, so it's a bi-matrix inequality, so it's not a perfectly convex, so you have to use some short relaxation to turn this into a convex optimization problem. But still, you can do that, and it's very easy to show that because we are rigorously using some stochastic, nonlinear stochastic stability theorem to really minimize the steady state error, estimation error. We can easily show that this actually easily outperforms the extended Kalman filter in terms of inconsistency and also estimation errors. So that's the paper, Observer Design for Stochastic Nonlinear System via Contraction-Based Incremental Stability, published in the Transactions on Automatic Control 2015. So why am I talking about this in this talk? Here, I want to kind of send you a message here that when you actually combine machine learning-based method like some box, like a black box, either used for nonlinear control or estimation or motion planning, you can make sure that the combined system is stable. Then you might actually have to resort to some nonlinear stochastic stability theory. That's what I'm talking about here. So in the new paper that is under review and was published in the CDC with Hiroyasu Tsukamoto, we actually improved our convex optimization methods so they can better predict the actual mean squared error between the desired trajectory or estimated trajectory or an actual trajectory. So you can actually apply this to the control method so that you can actually have a nonlinear tracking controller that can minimize the steady state tracking error out of this rigorous nonlinear stochastic contraction number. So you can easily show that it easily outperforms the, its method is called the CV stamp. It easily outperforms the H infinity or PID controller, and you have to track the certain desired trajectory using stochastic nonlinear dynamics. So for this method, the still is kind of a learning-free method. We just use a conventional like optimization-based method to design the robust nonlinear controller or nonlinear estimator to either track the some desired trajectory computed from this learning-based method or estimate the state. But it doesn't really have a learning. So what if you add a learning for even for feedback control or estimation? So this is the new method I'm very excited about. It's actually just published in the IEEE control system letters. When you compute this deterministic stability, we basically sample the like a basic reappraisal function, and in our system using contraction theory, so it's almost like a finding control reappraisal function, but we kind of find our search into focus our search onto finding the optimal M, the contraction metric. So you train the M using neural network, using multiple samples that's computed from offline optimization, convex optimization I talked about earlier. And then you can train those neural network. That means that you don't have to solve this optimal optimization problem in real time because this neural network replaces the numerically computed M of X, like a Riemannian metric. So your reappraisal function looks like a delta X transpose M delta X. So that can guarantee certain stability of your nonlinear control design system. So this is a nice combination of a neural network with a rigorous nonlinear stability theory or nonlinear control design. So it's called the Neural Contraction Metric, where you actually use the LSTM, like a recurrent neural network, to train the M of X, and then we are using that neural network function M of X to design the nonlinear controller. And then you can easily show that it actually easily outperforms some of the other methods in terms of estimation And also we can also design this method for motion planning as well. In closing, I want to show you another example of combining machine learning with a motion planner. So it's called the GLAS, and this might be also useful for motion planning for dense forest, because we have to actually take into account the collision avoidance with other obstacles and also other neighbors, for example. So it's called the GLAS, Global to Local Safe Autonomy Synthesis. Maybe let me show this video. So idea here is that, yes, we can pre-train this multi-agent motion planner using expert demonstration, and expert demonstration actually comes from maybe, for example, some centralized optimal motion planner. And then we want to keep this kind of locality in the computation, so you still use a deep set so that we can actually mimic the centralized expert demonstration using a deep neural network. And then, so it's combination of that deep neural network that kind of mimics the centralized planner. And then you have a local safety filter to ensure that it's like a PD control with a certain barrier function or safety filter, so that they don't really collide with each other, while it's actually still follow some desired trajectory. It computes from the evaluation of a deep neural network. So again, deep neural network is actually based on deep set. It mimics some desired optimal trajectory you pre-compute using the imitation learning, using some expert demonstration. And expert demonstration here again is a centralized optimal motion planning. And then we can demonstrate that for multi-agent systems. So we kind of reviewed that some motion planning with the learning is for the input SNOC. So even using nonlinear dynamics and stochastic nonlinear dynamics and chance constraints. And then we also reviewed that how you actually design the robust nonlinear controller, but now what if you add a learning-based method to kind of replace some online computation or online convex optimization, because deep neural network can be evaluated so that you can actually mimic certain optimal solution. And that kind of method also is used for motion planner for the GLAS. And also I have showed that this stochastic stability analysis is actually critical to ensure some safety of your learning-based method for planning and control and estimation. So we also have shown you that neural contraction metric, which can incorporate some deep neural network to replace some optimization-based stability method. So thank you so much. And you can check our papers by checking out our website, aerospacerobotics.caltech.edu. So thank you so much for listening to my talk.